Okay, welcome back. We are beginning a new series or a new unit of study today. As I said before, as we move through these units of study, we're getting closer and closer to the basis of what chemistry is. In the last unit of study, we had looked primarily at what we would be considered excess baggage in chemistry, and that is the nucleus of the atom. Protons and neutrons, which live in the nucleus of an atom, really have nothing to do with chemistry and chemical bonding and that sort of thing. It's all about that important third subatomic particle, the electron. Electrons in atoms are what chemistry is all about. Frequently, or I refer to the chemistry as the dance of electrons, and their placement in the atom makes them amenable to leaving one atom and approaching another one, and so on and so forth to form ions. But the general idea is that electrons populate the area outside of the nucleus in a particular way, which may go against the sort of the common view that these electrons are orbiting around the nucleus, like planets orbiting around a star or something like that. It's more complex than that. But the way we're going to be laying it out is actually a more relaxed view than in many courses. So let's take a look at electrons in atoms. The best way to view the way electrons are placed or stacked around the nucleus of the atom would be to think about them at discrete, meaning a particular place, discrete and increasing energy levels. Now I use this n term, this lowercase n, for energy levels. So if we look here on the diagram, we have our nucleus right at the center. Electrons are added into energy levels. N equals 1 right here would mean that we fill up an energy level before we move on to the next energy level. Now, which is essentially what I said here, but that the distance, we have a distance between our energy levels. We fill the lower ones first, followed by the higher ones, and as each of these are successively filled with electrons, we go to the next higher and the next higher energy level to put electrons in there, depending on how many electrons are in a particular atom. Notice here that in our model, and this is going to become important, that the distance between these energy levels grows smaller and smaller. So here is a distance which is greater than the next distance from 2 to 3, say, or from 3 to 4, or 4 to 5. We get sequentially decreasing distances between energy levels. Now, we're going to find that within energy levels, we have sort of an address system to break down these energy levels further into what are called orbitals or subshells. So we're going to take a look at these different energy levels. So we're going to see that they're more complex than just sort of concentric spheres around one another, and we're going to be breaking them down further and further until we can get to a point where each electron within an atom has its own set of coordinates or its own address, if you will. So let's take a look graphically at how energy levels are broken down into orbitals. Notice over here on the left-hand side, we have our energy levels starting at the bottom because that's the lowest energy, n equals 1, n equals 2, n equals 3, and n equals 4. Now I said that energy levels can be broken down into orbitals. Let's look at this bullet point right here. The number of orbitals which an energy level can split into or has is the number of that energy level itself. For instance, energy level n equals 3 has 3 orbitals. So immediately, if we know what energy level we are in, we know how many orbitals we have. So let's look at energy level versus orbitals here. Energy level 2, n equals 2, well, that's 2 orbitals. Energy level 4, n equals 4, well, that's 4 orbitals. We know it because it's hiding in plain sight. It is standing right in front of us. Now, these orbitals themselves are labeled. Now, they're specified by letters in the following order. And let's look at this, how it goes. It goes an orbital to p orbital to d orbital to f orbital in that particular order. Now, so s orbitals within an energy level always fill first. They'll fill first, followed by a p orbital, followed by a d orbital. It follows that general way we're looking at right here. So first of all, let me bring your attention to these lowercase letters conjure up any repressed memories of past chapters or past units of study? Well, they should. In the last unit of study, we looked at our block nomenclature in the periodic table. We had our S block, our P block, our D block, and our F block. We're going to find that those blocks actually are defined by the electrons within them. So the S block is defined by S electrons, P block by P electrons, and so forth. We'll get to that eventually, but again, we have some harmony here between what we've looked at before and now what we're learning just now. So we see that it's not all new material. We can lean back on that previous material and say, hey, there's some familiarity here. Now, we know that orbitals always fill low to high. So n equals 1 fills first. It fills first. Here we have an n equals 1 has only one orbital, and it must be an s orbital. Why? Because it always starts with s. We can't have a p orbital, which is the next one in that series, because we only have one orbital. We only have one s. Fair enough. That would mean when we fill that s orbital, energy level 1 is complete. And then we move to energy level 2. And we know that energy level 2 has a total of 2 orbitals within it. It always starts with the s, given as 2s, and then the p orbital, 2p. Look at what we're doing here. We filled all the way from energy level 1 to energy level 2, down on the bottom. Look at this. 1s. So that 1s orbital was filled, then we were done with the energy level 1, and we had to move to energy level 2. And that would mean that we then went to 2s, then 2p, just as we've done right here. So really what we did was we went from 1s to 2s to 2p, right? Then we're done with energy level 2. And if we still have electrons to stack around that nucleus, we may not, but if we do, then we have to start with energy level 3. And that energy level 3 has 3 orbitals, and they go 3s to 3p to 3d. Notice now. So let me just clean this up a little bit here and move forward. If we were filling in order that we were supposed to fill electrons within these orbitals, it would start with 1s to 2s to 2p to 3s to 3p and so on. So that as we have the whatever number of electrons we have to stack around a nucleus, we have these boxes or these areas available for them. They don't have to be filled, these orbitals. They can lie empty, but they lie available depending on the number of electrons that are necessary that we have to deal with. Okay. So the way electrons are arranged around a nucleus is a hierarchy of information, much like an address. And each subsequent part of an address, if you read it in a particular way, further and further focuses in on exactly where an electron should live, or I use the analogy, where I might be living. So if you asked yourself, where is Steve Flemmer right now? You could say, all right, well, he is in the state of Vermont. Technically true, but that's a pretty wide swath here. The state of Vermont is rather large, so we can say, all right, so you want us to be a little more complex, a little more focused. He's in Burlington, Vermont right now. And I would say, well, Thank you very much. That's very helpful. But Burlington is a large city, so maybe you could whittle it down a little more. So, all right, fine. He is at the University of Vermont in Burlington, Vermont, right now. And again, as you can see, we're getting closer and closer. But in each case, we bring that focus smaller and smaller. It's like, well, UVM is very large. Can you give me the building he's in? Sure, Innovation Building. He's in Innovation. It's like, well, maybe you could do me a solid instead of me walking all around Innovation Building. You could tell me exactly the name of his office, and that's where he would plunk himself. Sure. 331 Innovation Building, University of Vermont, Burlington, Vermont, and so on and so forth. That is a hierarchy of information. That analogy is going to be put to the hierarchy of information that we see in devising a specific set of coordinates that for each electron in an atom that is different from every other atom. So let's look at this from the ground up. We had looked before, and we always start with energy levels around a nucleus. Our energy levels n equals 1, 2, 3, and 4. And within these energy levels, they can have certain orbitals. Energy level 2 has 2 orbitals, and those are the 2s and the 2p orbital, because there's only 2 of them. Energy level 3 has the 3s, the 3p, and the 3d orbital, if you will, because it has 3 orbitals. So now what I would like to do is start to look a little more closely at what these orbitals actually can represent, if you will. And this now brings us into an idea or an area known as suborbitals. What do our orbitals look like? And are there different areas within these orbitals? That's going to become important, because if we have a greater number of areas or rooms, if you will, within each orbital, that can hold a different number of electrons. So with respect to suborbitals, the way they are expressed can be helpfully expressed much of the time are with respect to boxes, a series of boxes, the number of boxes, and so on. An s orbital always is represented by one box. One box. Why? Just is. One box. P orbital is always represented by 3 fused boxes. 3. A d orbital is always expressed as 5 fused boxes. Now notice there was also an f orbital. F orbitals, we're not going to really look at that because they occur very, very low on the periodic table. And remember when we said as we go down that periodic table and look at elements within them, their reactivity becomes less predictable because they become more complex. And in this course, we like predictable. We're going to try and make things as the least complex as possible, which is why we're not really even going to be discussing f orbitals. But we can see the trend here. We have 1 box to 3 boxes to 5 boxes. If we were to go that trend, it seems like we're adding 2 extra boxes. What would an f orbital look like? Well, add 2 to the 5 boxes we see here, and it would be 7, and you would indeed be correct. We're not going to look at those, though. Now, why do I put boxes here? Is because of the electron occupancy which is allowed in each of these boxes, in each of these suborbitals. There are always 2 electrons per box shown in the model that we're building right here. Notice I have 2 sort of fish hook arrows, if you will, in each of the boxes. That means that in each box we don't have to, but can hold a maximum of 2 electrons. 2 electrons. And most importantly, or not most importantly, but of extreme importance, is that since every electron has to have a different address or a different set of coordinates within an atom, notice how I write these within 2 electrons to a suborbital. Notice how I write them. One with the fishhook arrow pointing up and one with the fishhook arrow pointing downward. That is to show what is considered spin S-P-I-N, spin of an electron. That doesn't mean one electron is spinning like a top in one direction or spinning like a top in another direction. It's a quantum mechanical designation, but what it ultimately means is that the electron here on the left-hand side is different than the electron on the right-hand side because they have two different spins. We are not, as a class, going to be getting into describing specifically what spin is, but rather to use one with a spin up or a spin down that separates the two electrons into two different sets of coordinates. So overall, each electron's address starts with energy level, then we go to orbital, then to suborbital, and finally to spin. And each electron is going to have a different panoply of these different coordinates. So we know we have the capacity for around an atomic nucleus to stack electrons or to place electrons, but we have to have a way of expressing that in a way that we can communicate with one another. And there's two ways of doing that. One is more of a language-based way or a written way, and another is more of a pictorial representation of that same exact electron arrangement about a particular atomic nucleus. Now I'm going to be showing you examples in here where we haven't really gotten to the point where we can understand these examples, but these are just for show, and in ensuing slides we're going to be looking at how to bring about these or how to write these in these two very separate ways, a written language and a descriptive language. So let's look at the written language first. A written description is known as electron configuration. Electron configuration is also known as subshell notation. Those are interchangeable, and I'll probably be bouncing between the two terms as we move along. An example would be what we see right here. Notice that we haven't talked about how to get to this, but this is an example of an electron configuration specifically for the element fluorine. 1s2, 2s2, 2p5 is the way that's written. We have some things that look like exponents in there. They're not actually exponents. It's just a way of expressing these. We have numbers and letters in there, but we will be talking about how to express, to draw these and express these as we move along. So that's the written description, sort of the written language. The more pictorial description is known as an orbital diagram. And whenever we're writing an orbital diagram, we go back to those boxes. We go back to the boxes which defined our different orbitals. Remember, an s orbital was one box. A p orbital was 3 fused boxes. A d orbital was 5 fused boxes. So these boxes, these fused boxes, are exactly how we're going to be expressing an orbital diagram. This is a representative orbital diagram. Again, for the element fluorine, we're going to see how these are put together, but notice we have depictions of these boxes, and especially important, we have labeling on these boxes, and because we've seen this progression before, 1s to 2s to 2p, is how we looked at that before, 1s to 2s to 2p. We fill those with respect to increasing energy levels and the orbitals which are contained within them. So let's look at the electron configuration as well as orbital diagrams for the first 10 elements. And to do this, just to give us some picture to work with, up here, notice that I have sort of taken the top 2 rows of the periodic table and left the rest. It looks sort of weird, but these are exactly how the top 2 rows of the periodic table would be expressed if we were to just cleave off those top of them. Notice, remember, we read the periodic table like lines on the page of a book. And when we do so, we have an increase, a sequential increase in atomic number. 1 to 2, then 3, 4, 5, 6, 7, 8, 9, 10. Notice that atomic number now, that corresponds to the number of protons in each of those atoms' nucleus. I want to expand that. Since we're talking about atoms of neutral elements that we're going to be giving electron configurations for, since in a neutral atom we must have the exact same number of protons as electrons, we can use in this instance our atomic numbers, which normally designate the number of protons, as the number of electrons that we have to work with in this special case. So notice, again, we are dealing with neutral atoms. So for instance, the first element here is hydrogen with atomic number 1. That means there's 1 proton in its nucleus, and to exactly balance it out to neutral, there is 1 electron, and that is the electron that we're going to be working with right now. So let's look at this. That first, we have hydrogen. And so hydrogen is here, H, chemical symbol H, and the number of electrons, 1. Now, electron configuration, 1 for energy level 1, S, because that that first orbital within that energy level is S1, given as a superscript. Must be a superscript. That by definition, we have to have that. And that is, since we only have to account for 1 electron, that is it. We're done with this one for electron configuration. Moving over to the right for an orbital diagram, we start with energy level 1 with an s orbital. That means an s orbital must be 1 square. And since it's only 1 electron, as we saw over here, we're just going to put 1 fishhook arrow in there. Just 1 fishhook arrow. And that would be the orbital diagram for hydrogen. It's very, very simple at these early stages. But we're going to move on and now start talking about the second element. Move all the way across that line to the end of that first row, only 2 elements in it. And we have helium with atomic number of protons, 2, also number of electrons, 2. So we now have 2 electrons that we have to deal with, and so we will. Again, we are 1, energy level 1, S, but that s orbital can hold 2 electrons. So we're 1 s2 for the electron configuration of helium. The orbital diagram for helium is given here, is still that 1s orbital, but now we have another electron in there, spin down. So this would be the orbital diagram for helium. Again, when in doubt, read the periodic table like it's lines on the page of a book. So we were finished with that first row on the periodic table. Now we go to the beginning of the next row with lithium. Has atomic number 3, that's 3 protons, also 3 electrons, so we have to account for those 3 electrons. Well, it's really, as we go down this series, it's exactly what was there before, plus 1 electron. So as you can see here, we had 1s2 for helium. Well, we have 1s2 for lithium, but we have to add another electron. That s orbital, the s orbital is all there is in that first energy level. So then we have to go to the second energy level and start that with an s orbital, 2s1, as we see up top on that superscript right there. 1s2, 2s1. Now the orbital diagram for this is exactly what we had before for helium. We just move it down there, but now we're done with that first energy level because it only has an s orbital, and we have to go to the second energy level, which starts a new s orbital. So we draw that in and put in 1 fishhook arrow. Next one, we can sort of move along here. Beryllium. Beryllium with atomic number 4, 4 protons, 4 electrons. So 4 electrons is what we're going to be putting in there. Notice what we had before on electron configuration, we're going to be putting right down here and adding 1 electron. Instead of 1s2, 2s1, 1s2, 2s2 now. And that will finish off our next s orbital. Orbital diagram, written as shown here, exactly what we had up top here, but notice we're just putting another fishhook arrow to finish off that 2s orbital as we see in here. Next one, boron. Wow, that means we got to go across some empty space. Reading the periodic table like lines on the page of a book. Here is boron. Okay, 5 protons, 5 electrons. 5 electrons is what we're dealing with. And notice now we have our exactly what we had here. We're bringing down there, and now we have to add another electron. We recognize that the 2s orbital, that second energy level, has been filled. So what next? Well, we know energy level 2 has 2 orbitals, an s, then a p. Oh, so now we bring in our p orbital. Our p orbital, 2p, has 1 electron in it. 1s2, 2s2, 2p1. Again, everything for the orbital diagram, everything we had up top, we put down on the bottom, and we just had to add something new, a whole new scaffold, really. The p orbital with its 3 suborbitals within. We have to put that whole thing in there. The whole thing has to go in there. And right now, we have our 2p orbital with only 1 electron in it. And that's fine. That's fine. There's only 1 electron we have to deal with. So we could ask, let me ask the question before we go to the next series. If I showed you an s orbital, how many electrons can fit in it? Now, obviously, an s orbital is 1 box, so it can only fit 2 electrons. Fair enough. If there's 2 electrons per box, how many electrons can fit totally in a p orbital if it was totally full? Well, 2, 4, 6. It can accommodate up to 6 electrons. In this case, we've only used up 1 of those, but as we move along now, we're going to be looking at continuing to fill up this 2p orbital. So let's continue. We were at boron with 5, and we're going to move over to carbon now with 6 electrons. So let's look at that. 6 electrons, exactly what we had before, add 1. On the previous one, on boron here, we had 1s2, 2s2, 2p1. Well, I'm just going to add another electron to that p orbital. Now it's 2p2. Because I just showed you that we can have a total of the number 6 up there. Total of 6 electrons. Okay. So here now we have our orbital diagram where we've just added another electron to our p orbital. So now comes a rule. Now comes in a rule. When we're looking at an orbital with multiple suborbitals, the rule is we fill the boxes singly first. Singly. Which makes sense. If you moved into a 3-bedroom apartment and you took 1 room and then you got a roommate coming in, would you have your roommate move into your room, or would you have your roommate take one of the empty rooms? Have them take one of the empty rooms. And the same is said to be true with orbitals with multiple suborbitals. Notice that next electron in that orbital diagram goes into an empty room until it can't anymore, until all the empty rooms are full. Then we'll start doubling up. Fair enough. So we just looked at carbon. Now what's next to carbon? Well, that would be nitrogen with 7 protons and 7 electrons that we have to stack. Exactly what we looked at before, but we're adding 1 electron. Notice that superscript 2 goes to superscript 3. Superscript 2 to superscript 3. And when we're looking now at our orbital diagram, we added an electron singly into that last empty room. That would be the orbital diagram of nitrogen. So we're plugging along here. Let's look now, we're going from nitrogen up top to oxygen, where we have 8 protons and 8 electrons. Well, we went from P2 here to P3. That means we're going to go 2p3 to 2p4. Why? Because a p orbital can hold up to 6, as we saw before. Now, notice on our orbital diagram, we filled up our empty rooms with one. We filled singly first, so our next electron has to double up. And here it is. We're doubling up that electron into one of the rows. We have to do that. After we fill singly first, we have to do that. Fair enough. We're plugging along here. We're almost at the end of a row. Going from oxygen then to fluorine with 9 electrons, 9 protons, 9 electrons, so that's 9. Notice on our electron configuration, it's exactly as it was before, except instead of P4, we went to P superscript 5. 1s2, 2s2, 2p5. Our orbital diagram, we see we've added an electron spin opposite, as we have before, in that room now. So that's different. That's great that it's different, because all electrons have to have a different number of, or different set of coordinates, if you will. So lastly, what we're going to do, we're at fluorine, and we're going to finish ourselves off with that 10th element, neon. We've got to the end of a row. It's going to be something very special about being at the end of a row. But we'll talk about that later. That's 10 protons, because atomic number 10, also 10 electrons. Look what we've done. We have finished off that row on the periodic table. We've also finished off that energy level, 2p6. We can't fit any more electrons into that energy level. And now look at this. We've added our last electron to that p orbital, doubled it up, the spin the opposite way, so that we have indeed moved through the first 10 elements with electron configuration and orbital diagram. Further elements, the electron configuration and orbital diagrams for, are just an addendum to this. We just continue adding on. So we had just finished talking, or I had just mentioned about the importance of completing an energy level, or rather completing a row on the periodic table. Now, it turns out that when we complete a row on a periodic table, as we read one line on the page of our book, that analogy, we have completed an energy level. So here is yet another emerging pattern within the periodic table that dovetails very nicely with this idea of energy levels. So a completed energy level corresponds to a completed row on the periodic table. Now this is called, by definition, a loose definition, it is called an octet. An octet. It means we have completed an energy level. It's not always the case, but oct is the term for 8. It's a term for 8 elements. And we're going to, and a row on a periodic table always ends with a noble gas. Now, a noble gas has what is considered as an electron configuration, a noble gas configuration. A noble gas electron configuration. That might seem obvious. Let's look at those two top rows on the periodic table again. I'm going to cleave up our periodic table just to look at that. The first two rows on the periodic table are the first two energy levels. And let's look at that. Now, as we read across a row on a periodic table, as we get to the very end, that shuts off an energy level. That's the first energy level completed. Then we have to start the next energy level to put electrons in, which is exactly what we did in the last slide or so, and we finish off another energy level by getting to the end of that row. Now, the term octet came from, generally we're talking about 8 elements. Here on this second level, our second row, we indeed go through 8 boxes, 8 elements going all the way across the row. That is an octet. Now, first of all, for the most part, we're talking about working with only the S and the P blocks on the periodic table. That is the two peripheries, if you will, on either side are the S and the P blocks. So if we were to look at the first row on the periodic table, there simply isn't enough elements because there's not enough places to place an electron in that first energy level. So frequently the octet on the first energy level is known as a duet. A duet. It essentially means the same thing, an octet or a duet. It means the end of a row on the periodic table. It means the end of an energy level. It means a noble gas electron configuration. And we're going to find that a noble gas electron configuration is very, very stable. Noble gases, they're noble. They don't form ions. They don't want to give up electrons or take on electrons. They're very stable the way they are. So if we look at this in a sort of a tabular fashion, the list, those 10 elements we went through last time, it's not that important, but really as we go through the elements, as we see right here, that first row, it ends the first row right here. We had that full duet, and then we started the second row, and then went all the way down it until we achieved that full octet. So it's just two different ways of looking at it. I prefer the way up here, this cleaved off portion of the periodic table, because it clearly shows that when we finish a row on a periodic table, we are completing an energy level, n equals 1, n equals 2, and so on. So let's see if we can't try and notice a few more patterns in the periodic table. I have a periodic table right here, sort of below our offerings, if you will, of our energy levels and orbitals and even suborbitals. So the first thing I want to do over on the left-hand side is to note that our first 4 rows on the periodic table correspond to the first 4 energy levels: n equals 1, n equals 2, n equals 3, and n equals 4. The second thing I want to illustrate is that these energy levels are comprised of orbitals, which in themselves have different shapes, if you will. An s orbital is 1 box, can hold 2 electrons, right? A p orbital is 3 fused boxes, can hold 6 electrons. A d orbital is 5 fused boxes, which can hold 10 electrons, 2 per box. So let's now start looking at the shape of the periodic table. I am going to circle, and this is going to sort of move back into our discussion of the block nomenclature of the periodic table, the S block, the P block, the D block, and so on. Let me just generally circle the S block on this periodic table. The S block is how many elements thick? Well, it's 2. There's 2, 1, 2. Anywhere you go in the S block, 1, 2. And so the S block is 2 elements thick. How many elements can fit in an S orbital? 2. 2 electrons in an S orbital. S block, 2 elements thick. Coincidence? I think not. Let's look at it backwards. In a p orbital, how many electrons can fit total in a p orbital? 6, 2 per box. How many elements thick is the p block on the periodic table? You will find that it is 6 elements thick. Again, coincidence? I think not. Maybe see where this is going. A d orbital can hold a total of 10 electrons, 2 per box. How many elements thick is the d block on the periodic table? You got it. It is 10 elements thick. So here now we can specifically take a look at the periodic table and now start to make some sort of sense as to its shape, at least with respect to the thickness of the S block, the P block, and the D block on the periodic table. So again, if we look down on the lower left-hand side, we can put this more specifically. There, down on the lower left, there is our S block. That holds 2 electrons. Let's look over to the P block. Well, that holds 6 electrons. And indeed, our D block holds 10 electrons because of the electron occupancy ability of our 3 types of orbitals. So if you'll remember when I told you that as we look at elements further and further down in the periodic table, things get less predictable. And we're going to see that now by showing that overlap, we get ultimately, since our energy levels around a nucleus, as we move out from the nucleus, the distance between them gets smaller and smaller and smaller and smaller. Eventually we get an overlap in these energy levels. They overlap with one another, which make things less predictable and more complex. We don't like complex, we like predictable. But we're going to see how the shape of the periodic table shows this overlap. And this first slide is going to lay things out for us. And what I've put over on our right-hand side right here is a rendering of how our energy levels are broken down into orbitals and subsequently the suborbitals. And over on the left-hand side is our periodic table. So let's, as we said before, when in doubt, we read the periodic table like lines on the page of the book. And we're going to find that the number of elements in each row corresponds to the number of possible electrons in an energy level. Let's look over to the right-hand side. Energy level 1 has 1 orbital, and that's an S. How many electrons total can fit in energy level 1? Well, an s orbital can only hold 2 electrons, and that's it. So in that first energy level, that first row of the periodic table, there are only 2 electrons, thus only 2 elements. Great, and we've finished that energy level. We start a new energy level by the next row on the periodic table. Look over again onto the right-hand side, energy level 2. What do we got in there? Well, we have a 2s orbital and a 2p orbital. Okay. How many electrons fit in an s orbital? 2. How many electrons fit in a p orbital? 6. Total of 8 in energy level 2. Let's see. Rolling across the row. 1, 2, empty space. 3, 4, 5, 6, 7, 8. 8 elements in that row. 8 electrons in that energy level. All right. So as we move along, again, if we start the next row, that's the 3rd energy level. There should be in energy level 3, there's an s orbital over here on the right-hand side, a p orbital and a d orbital. They do exist, but eventually we are going to find some overlap. So if I started here, 3s, empty space, 3p, and so on, we finished that row. Now notice, we finished a row, but we didn't get to that D, 3D. This is the result of an overlap in energy levels. Where do we start? Well, if we had to, here's now the 4th row on the periodic table over here on the left, 4s. What's going on? We missed 3D, which must have come first. Let's take a look at how this is going to spin out, and we can explain that by the overlap of energy levels. So we'll see that on the next slide. So let's look at an extension of our energy levels as we go from bottom to top, increasing energy. So here we start at energy level 1. We go 1s, 2s, 2p, 3s, 3p, and we should end up with a 3d here. But what instead happens is we start with, we have 4s in between 3d, and we sort of we hopscotch each other. That means that the fourth energy level starts before the third energy level is completed with respect to the placement of electrons. So this is the area where we get that overlap. And I should say that as we increase in energy level, that overlap becomes more and more intense, and it gets very, very confusing. But here is that first overlap. And let's look at this, we'll blow this part up here. And we see now that as electrons continue to add into or around a nucleus, they're not really rule followers. They're just looking for the next lowest energy level for them to go into, or sub-energy level, as you will. So imagine electrons filling up the 3s orbital, then to the 3p orbital, and they fill that up, and then we need to add another electron. And the electron is looking, it's like, oh, I should go to the 3d there, but the 4s is much more, is much closer to me in energy, so I'm going to be a rule breaker and go to fill 4s first, and then I'm going to fill 3d, and then fill 4p. It matters not to me to follow the rules, says the electron, but rather which energy level is the next up and more easily attainable. So if we looked at this on the whole, we see that, or as far as a summary, we've seen this overlap between the third and the fourth energy level. Indeed, the fourth energy level begins before the third energy level ends, and we're going to see how this tracks with the periodic table. The overlap in these energy levels becomes greater, so that there's more overlap as we go up in energy levels, which is why with those elements at the lower end of the periodic table, we just kind of say, time out, we're not really going to be dealing with that. But let's take a look at how this overlap actually manifests itself in how we read the periodic table. So try and bear with me here, because I'm going to be trying to juggle two diagrams at a time. Notice here on the right-hand side we have our energy levels as they're shown. It's from the previous slide. We're not going to go this high in energy levels, but let's now track the periodic table, and I'm going to try and mention each time we go through a new orbital. 1s, 2s, 2p, 3s, 3p, and 4 on. So let's look over here on the left-hand side, and I'm going to just start reading the periodic table like lines on the page of a book, and this overlap will emerge. So here we go. Energy level 1, S, completed. Energy level 2, 2s, 2p, completed. Energy level 3, 3s, 3p. Next line has to be 4s, because we've already done 3s. That has to be 4s. The next thing, where the D block actually comes in for the first time, has to be 3d. Why does it have to be 3d and not 4d? Because by definition, the third energy level is when the D block, or the D orbital rather, appears for the first time. So this must by definition be, and follow me again on this, 4s, 3d, 4p. That is exactly what we see on our piece right here. 4s, 3d, 4p. And we've made that logic argument that that first line in the D block has to be 3d, because that's the first time that it's ever shown. A common mistake, if you will, would be the following, would be to go, if you'll follow me on this fourth line now, 4s, 4d, 4p. It's not. It's 4s, 3d, 4p. And that's how we follow these as we're coming to terms with perhaps expressing electron configurations for the heavier elements, or certainly out of the second row on the periodic table, which we'll look at next. So here we're asked on 3 examples, phosphorus, iron, and sulfur ion, to draw the electron configuration and the orbital diagram for them. The first one, phosphorus. First of all, in any of these, we have to look on our periodic table, our trusted periodic table, to find what we're looking for, phosphorus. That atomic number 15 above the chemical symbol of phosphorus means that we have 15 protons and 15 electrons in that neutral atom. So we have to account for 15 electrons. Now, really, we can just move straight across the periodic table here in order to complete this. So our 1s, 2, 2s2, 2p6, 3s2, 3p1, 2, 3. When in doubt, use that periodic table. And indeed, that's what we have. If you want to check your work, you can look at that number, 15 electrons, and just add up these superscripts right here, and it should come out to 15. If it does not come out to 15, then there's a problem. But indeed, that is how to check your work on these frequently. So now for the orbital diagram, we essentially just have to start drawing boxes. S orbitals are one box, p orbitals are 3 fused boxes, and so on. Always important to label them. 1s, 2s, 2p, and so on. Don't just leave them unlabeled. But once we do that, what boxes do we draw? Well, we find we have the answer right here. We got an S, another S, a P, an S, and a P right from the electron configuration, and that is how we express those boxes below. Then it's just a simple matter of filling up with 15 electrons as we see here in this orbital diagram. Note, of course, that in the final case, that p orbital has three electrons in it. They have to fill singly first before we can start doubling up. Okay, next one, iron. Let's find iron in the periodic table. There it is. Now, this is the first one we found in our D block, but again, we just use the periodic table lines on the page of a book, and that's all we're going through there. Appears to be 26 is atomic number, so that's 26 electrons we're going to need to find. So, and again, I know this gets boring, but I'm going to do it anyways because it works. 1s2, 2s2, 2p6, 3s2, 3p6, here we go now, 4s2, 3d, 1, 2, 3, 4, 5, 6. There it is. So remember, we're encountering that overlap. That overlap there allows us to go from, 1s to 2s to 2p, 3s, 3p, 4s, then 3d. We can use these S, P's, and D orbitals in that order to map out our orbital diagrams. Now clearly we have that n equals 4 beginning for n equals 3 energy overlap. We also on our orbital diagram notice that we have some filled doubly, some filled singly. So all of these are important considerations. The last one, let's look down here in the lower left-hand corner, sulfur ion. What is a sulfur ion? Well, what is the predicted ion that sulfur forms? Let's locate sulfur on the periodic table here. And in our, if you remember in the last unit of study, we had our predictable ions. So noble gases are 0, halogens are -1, and in this column, which sulfur resides, that is -2. So sulfur is going to be S2-. That means let's seek out sulfur again here on the periodic table. And there it is. And look at that number right above it, 16. That is the atomic number. But down here in the lower left-hand corner, that negative 2 there means we have 2 more electrons in there because electrons carry the negative charge. So that has to be 16, 17, 18 electrons. So really, notice what we're doing here. The 18 electron element is argon. So really what we're doing for drawing the electron configuration for an orbital diagram for sulfur ion, we're really drawing it for argon. And indeed, that's what it is. What this electron configuration and the orbital diagram here is the is that for argon, because we have 2 extra electrons. I'm bringing up a fancy science word here down on the bottom. Notice that sulfur ion is isoelectronic with argon. We're going to hear that term isoelectronic. Iso means equal, electronic means electrons, so equal number of electrons as with argon. Okay, finally, last slide of this lecture. I know this has been a long one. Is that I want to introduce a shorthand way of expressing the electron configuration. Remember, 1s2, 2s2, 2p6, and so on. It's a shorthand method, meaning it's abbreviatory. We don't always have to draw out these very, very long electron configurations, but we can abbreviate them somewhat. So it's a shorthand method of expressing this subshell notation or electron configuration using the concept of noble gas cores. That is a core of electrons with a full octet. It is essentially the closest noble gas which preceded the element we're drawing the electron configuration for. Let's give an example. Magnesium. Here is magnesium on the periodic table, 12. It can be written 1s2, 2s2, 2p6, 3s2. And we would know that if we went across the periodic table, reading it like lines on the page of a book. But we're going to recognize something, that if you look in this box right here, neon, which precedes, that's the noble gas which precedes magnesium, neon, let's find that, there it is right there, is most, if you will, of this subshell notation. Indeed, neon is this much, and what is in the currently open energy level is that much. So if neon is what we see right here, this whole piece can be taken out and replaced with the elemental symbol of neon and brackets. Brackets, not braces, not parentheses rather, but brackets. So there are 2 ways of expressing, accepted ways of expressing this subshell notation or this electron configuration. We can do it the old-fashioned way, or we can do it with sort of a contracted, abbreviated way using a noble gas core if we feel like it. Let's look at another one. Titanium. Okay, now we're heading down. We have 22 for a number of electrons. So now that's a significantly longer one. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Notice I did that overlap. I hit into the 4th energy level and then went back into 3d. In any event, let's look at what noble gas precedes titanium. Titanium is right here in this 4th level, so let's go all the way back and we find that it is indeed argon. It's the nearest noble gas which precedes it. Fair enough. So if argon here is what we see right here, 1s2, 2s2, 2p6, 3s2, 3p6, we notice that most of titanium is exactly that. So we can, instead of writing all this extra gibberish right here, we can put in just argon in brackets and then complete that with 4s2, 3d2, if we want to. That can happen for any number of elements that you're drawing subshell notation or electron configuration for, but it is a shorthand way of doing it so that we all don't get a carpal tunnel syndrome trying to draw out an electron configuration that is very, very long.